Hi everyone, welcome to Untitled Data Science. So last time we have seen several models, including regularized models, support vector machines, naive Bayes, and other models. And we have actually developed with TF-IDF and with simple frequency count, and we have seen all the prediction algorithms. And we have actually seen some of these models performing very well. For example, elastic net, or with TF-IDF, or using the simple frequency, we have seen it's actually very sensitive and it's very accurate. Although individual models, they have already performed very well. I mean, we can choose one of the best models and you can deploy it to your real-world problems or something. But again, it's also possible to combine all these predictions and make a nice model out of all these models. So for today, what I want to talk about is combining predicted class labels, because I want to combine them. Because let's say one model may say something, an abstract. Remember, we are working on COVID and SARS abstracts. So one text classification model may say is a COVID, the other one may say SARS. So there may be this kind of disagreements among the models. But if you want to, you can, instead of choosing one best performing model, you can combine the predictions and you can still improve your classification. You can have like close to 100%, and that's actually by combining the predicted models. There are other complicated ways of creating ensemble models, but you can also do individual models, and you can in the end combine the predictions. You can just combine the predictions by several methods, and these methods may be majority voting. One is majority voting, so if more than half of the models say, let's say in our case, we are classifying COVID, we are saying COVID and SARS. So if a model says, let's say if you have 4 models, and if 3 of them say COVID, so that means the ultimate class label of that abstract would be COVID. But if the other one will not be SARS, because majority of the models are. So you always have to look is 50%, at least more than 50% of the models should say something. So this is actually something like the majority voting in presidential elections or something. So you take the majority vote. The person who has got the majority vote will be the winner. So that means the vote, that's in our case, for example, if 50% of the votes are COVID, so then it will be COVID. The other one is anonymous voting. So all should agree. So that means all models should say COVID. Let's say in our case, if you implement 5 models, 5 of them should say this is COVID. So then you accept it as COVID. If any of the models say it's not COVID, then you take it as SARS. The other one is weighted averaging. That's weighted voting. So you weight by some kind of performance, let's say by accuracy or sensitivity or specificity, depending on what you want. So you can simply average them by how to calculate weighted average. So that means each of the algorithm will carry some kind of weighted value, and then you multiply the prediction by that kind of weighted average. So let's say if you have 4 models, and one may account 0.75 if it is let's say 0.75, and the other one may account only 0.2. The other one may say, okay, it may account something 0.3, actually 0.2. Maybe let me do this. One may account 0.6, the other one may account about 0.4, and depending on the performance of the model. Let's say if you have a highly accurate model and then you want to weight that model to have a larger account. In the end, all of these models should have a summation of 100% in the end, or 1, so 1.0. So that means you multiply all of them by 1. I mean by each weighted average. So you have 0.6, the remaining will be 0.4. That means we have 4 models. One would be 0.2, and maybe the other one would be 0.1 and 0.1. So all of them, they will end up into 1. So that means each predicted class you will multiply by these values, and then you create. We'll see how to do that. For example, here recurd is predicted by 3 models. Let's say model 1 is support vector machine, model 2 is elastic net, model 3 is let's say naive Bayes, and two of the models are saying COVID and the other one is saying SARS. In our case, in using this 50%, that means it would be COVID. But if you have a model that says, if you say this one is the most accurate model, so then you give it the highest value, like 0.6, let's say. But if this one says, if this one is again the second most accurate model, so you give it around, let's say around 0.4 or 0.3. And if the last one is less accurate, then you give it a small proportion. So that will be around 0.1. So then the prediction levels will be multiplied by these values. That's if you do the weighted voting. But if you use the unambiguous, the unanimous voting, so that means all of them should agree. All of them should say COVID. Otherwise, you will classify it as SARS. That's what the unanimous voting, the unanimous, actually unanimous, not unanimous, it's unanimous voting tells us. So what I want to do is I want to combine all these models. So to combine them, so if you remember, let's say conf-mat, I have so many confusion matrix, I have already loaded them, and then let's say, let me see, I have, for example, conf-mat, conformant elastic. So I have all of this. But what I want to do is I want to combine all these predictions. So for example, if you remember product class, I have so many product classes. Should be my bias, I guess. But let me see. Or I can just print it out and see. So we have so many papers, and all of them they have some kind of label 1, 1, 0, include, exclude. Yeah. And so to do that, the first thing I want to do is I want to create predict ensemble. Let me just call it ensemble, and for that let me replicate and then replicate the exclude classes, and then I will replace the exclude classes later on by include, depending on how the modules agree to each other. So let me call it excluded. No, I'm not actually exclude. COVID. No, the other one, the negative case, SARS. And the next one would be I will take the links of how long this I'm just creating an open data set. It's kind of data sets that I'm creating the prediction in them. So then I will label everything by stars, but later on I will change it by the number of algorithms. So the links should be around like the test should be the links of my data test include. So that would be my actual class. This is a predictor class. So if I take this, everything should be no include. So if I show you this, I will have I think I have a certain number of testers. Let me just count. Maybe row test. How many do we have? And row. I have 294 cases. So that means if I run this, I will have this spread ensemble, and all of them will be labeled as excluded. I mean, as actually as SARS. So all of them are SARS. So like by now I'm already labeling them, all of them to be SARS. But later I will change the SARS label into COVID or something, depending on my algorithm. So the next one would be I will predict the included ones. Predict SARS, now COVID actually, and then from there I want to do this majority voting. Like majority voting, I will have to use the majority vote, and then for the majority vote, what I use is the 50%, more than 50%. So to do that, I will not weight them. I will give all of them as equal vote. So then the equal vote will be assigned by 1 times. So if it is not equal vote, I will simply multiply this by 0.6 or 0.1 or 0.3. But I will not weight them, but simply I give them with 1. That means all of them will account the same. So let me call this predict class. Let's say I don't know which of them I want to actually, because I have several models, but maybe let me just choose. But this is just for the demonstration, but in your case you have to carefully select all your models depending on their performance. And sometimes I have like SVM, for example, I have SVM sigmoid and SVM sigmoid TF-IDF and all these values. So that means the models, they are naturally correlated to each other because they are from the same algorithm. And then let's say SVM sigmoid TF-IDF. So they are not independent because of one algorithm. They are independent, but they are highly correlated because they are from the same models. So that means when you choose, you probably have to choose carefully and at least compare the two models and take one best performing algorithm. So let's play. Let's simply average SVM sigmoid. I'm not taking the other ones. So SVM sigmoid was actually our best performing algorithm, if I remember correctly. And then let me take ElasticNet, and what else? Maybe Lasso. Maybe let me still SVM linear. In the other algorithms I can still find out. So let me just call that prod class, maybe SVM, linear SVM. Actually, I can also take linear SVM. So I have linear SVM here, but I can choose one of them because they are highly correlated to each other. But I can also, I think for this demonstration, I will simply take all of them. So let me simply take prod linear SVM equals. So if prod SVM equals say COVID, so then I will label it as COVID. So let me get this off because my PC seems to be restarting otherwise. So let me just turn this off, this reminder. And then, so this model would be SVM linear, but I also have SVM TF-IDF. So I can simply take this, and actually I can add all of them. So I can take add plus, so let me take this here, and that would be SVM linear TF-IDF, I suppose, yeah, TF-IDF. So that will be the TF-IDF version of our model. The next one, let me just call another model, maybe SVM sigmoid. I can actually call all of this and replace few things. Sanakunda, is it? Or at least the structure. So SVM sigmoid tree. So this would be sigmoid SVM, sigmoid SVM, and again this would be sigmoid SVM TF-IDF. And now let me add another one, maybe lasso and elastic net. I can still add the other ones, but then I will change few things. What should I call this? Okay, prod elastic net, prod elastic and prod elastic TF-IDF. So let me call this prod elastic, and then again I have prod elastic net TF-IDF. I can still call lasso, doesn't matter. So let me simply change again a few things. So let me call this prod lasso. Where is prod lasso? Okay, prod lasso here, and again prod lasso TF-IDF. Prod lasso TF-IDF. So now how many models do I have? 1, 2, 3, 4, 5, 6, 7, 8. So that means I need 50% of the models. That means I need 4 models, at least 4 models should 4 algorithms should agree that something is yeah, it's COVID. To say COVID, 4 models should change. I mean, should agree. Otherwise, I will label it as SARS. I will not change this for example, the one I showed you before. So I will simply turn it off. So it will stay like that. Now, the last thing I want to do is now I already will have all of these values, and then I will replace that one with this. So to do that, what I need is I need to call this one prod ensemble, because I want to replace the SARS values by COVID. If 50% more than 50% of the models actually agreed to label it as, as COVID instead of SARS. So then to do that, I simply call this in square bracket here. You can also use some other method. So that means I'm giving here. So you see, so if 1 times prod linear COVID, 1 times this, so I'm adding all of them, and now there will be some counts. So you know there will be 4, 8 or something. So then what I'm interested in is in 50% of the models. So that means I will only need 4% of, 4 of them. So I have 8 models, and if 4 of them are agreed, if this is because this one gives me 0 or 1. So is it COVID or SARS or something? So it will give 0 or 1. And then if all of them are agreed, then I will take this value. I will label it as what? As COVID. So that's what I want to do. So now after that, I will have all the labels, and then this thing will be updated. So prod ensemble. Let me actually run it, and then see how this prod ensemble looks like now. It will be updated. So now we should have more COVID cases. So I have like a SARS, COVID, and yeah. So I nearly have half of the cases are SARS, and half of the cases are actually COVID. Then let me actually tabulate it, and then so this will be 161. But if you want, you can also tabulate it with a test include, and that will be like this. So let me calculate. Let's actually do this confusion matrix. So let me do the tab class. I want to tabulate the 2. This is the one we just did here. So I just print this, and then tabulate. And then after that, what you can is you can kind of ensemble model confusion matrix for actually conformat for ensemble model. You can create for your ensemble model like a so then I will call simply my confusion matrix function, confusion matrix, and then after that I simply call my this tabulated class here. So tabulated class, and then I define my mode into everything, mode to everything. And my positive class is actually, you can define it, but you can also ignore it. If you define like your positive class as 1, and then you can define, otherwise if you reverse it, you have to define your positive class, and my positive class is COVID. So now I can print out my confusion matrix, we will run everything, and then print out my confusion matrix and see if the ensemble model actually makes a difference. So if you remember, the biggest model we have was actually close to 95%, so the ensemble is almost making the same kind of prediction. But you can also change this value. For example, if you listed, okay, you can say 1/3 of the model, then you may reduce this number to, let's say, 2, 3 or something, depending on your interest, what you want to improve. Let's say in this case, I'm all fine. I should stop here because it's with the majority. With the majority vote 50%, I have already achieved 95% and 98%. But if you see, let's reduce this number to 3. It's not 50%, of course, and then see how this would be. So now it's reducing. So that means there are disagreements. So that means it's 98% again 94. So we should be okay with the majority vote, and let me stay with that 94%. You can also as I said, these two models, especially all these SVM models, they are highly correlated to each other because they are from the same class. so the prediction will be more or less similar to each other, so there will not be much information. So instead, what you can do is you can compare all these models, and you can simply select one of the 4 models. But we also have like radial SVM. I didn't count it in this weighted averaging. And this averaging method is not weighted; it's actually majority vote. Yeah, you can do that, but this is just for demonstration purpose, and that's how you can do majority voting, 50%, and that's all. So you can somehow improve your models, but we can also see actually how much it was with compared to the ConfMath. I think it was sigmoid, which we had a best model, ConfMath SVM. SVM sigmoid, if I'm not exactly sure, but let's see. So we have 95%, 98%, 92%. Okay, let's see what the other one. 95, okay, 89. So that means we have improved the performance 92%. Actually, then it's not this one. Then maybe it's not the TF-ID version. Let me, because this thing is complaining that I need to restart it. Okay. Okay, so that means this is one of the best models that we have, 94%, 98% sensitivity, and then 91%. But you see, with Ensemble model, we have gained a little bit of specificity. That's why our accuracy also gets somewhat improved. So that's how you can combine predictions, but be careful here because the models are highly correlated to each other. So then you make sure to choose one of the because one model is depending on, I mean, it's not dependent actually, but they are correlated. At least the predictions are correlated to each other. So it's better to select one of the best performing models. But as you say, I mean, if you want, we can also do that. Let's say we can simply turn everything off. We take only the sigmoid SVM, and then in this case, let me see. Let's actually compare with a ConfMath for the elastic one. What we can do is we can simply print the ConfMath elastic and then see which model was actually the best one. ConfMath elastic, elastic native IDF, and see. Okay, this is elastic. Then the next one is elastic native IDF 9890. The first one is 9890. So it's exactly the same. So there is no much change between the two models. So instead, again here we can turn off one of them. Actually, we can turn this off and take the TF-ID version. Again here you can, let me arbitrarily change this. Simply take one of them and then remove this sign. So now I have only three models from each class. From Lasso, I only have Lasso, and then from ElasticNet, I have only ElasticNet TF-IDF, and then from SVM, I only have SVM sigmoid. Now I can add them. I have only 3 models, majority vote, so that means more than 1/3, actually more than 50%. So that means you can, because we have only 3 models. So 3 models, that means the majority vote would be greater than or equal to 1. No, greater than 1. So more than 1, because I only have 1 will not be counted. So then if I run it, and we will see how our classification performance improves. So yeah, so you see it's again 94%, 98%, but it's more or less similar to what we have seen in the elastic model. 98, 90, 94, 56. So that's how you can combine. But next I would like to show you how you can extract these labels actually, because we can kind of attach them. So if you remember, we have test data, the test DFM actually, DFMath. No, I want to DFMath. Okay. Okay, DF matched. This was our data. So this is match DFMath. So this is my data. So I have this, and then at the end of each, I want to attach for each algorithm. So whether it's stars or yeah, and then I want to create some kind of table, tabulated form, and then from there I want to calculate like flies kappa value, like agreement statistics if you have multiple raters. That's what I want to do in the next session. But for now, this is how you combine predictions. Thank you for now. I hope you enjoyed this class.